Hello and welcome to this video on waves. My name is Yasmin and I'm a tutor here at Tutor Impact. And this video is designed to give you an introduction into waves, what they are, what are the different types, and some calculations that you can use to calculate different things, different components of waves. Now, this is a popular topic on most physics syllabuses, so it's a really helpful video to get you introduced and familiar with waves. Now, your first question is probably, what are waves? So waves are one of the ways in which energy can be transferred between stores. So it's a way in which energy can be transferred between different places. Now, waves can be described as oscillations, and these are vibrations around a rest point. So waves is where energy is transferred from one place to another, and they can be described as oscillations, which are vibrations around a rest point. An example of this is where sound waves cause air particles to vibrate back and forth. So sound waves cause air particles to vibrate back and forth. And you can see here that we're having that vibration around a rest point. So sound waves can cause air particles to vibrate back and forth. And another example, which you can see, is ripples causing water particles to vibrate up and down. So ripples can cause water particles to vibrate up and down. Now, the direction in which these oscillations occur, so the different directions, is the difference between longitudinal and transverse waves. So in longitudinal waves, the vibrations are parallel, so they're parallel to the direction of wave travel, and that means they're going the same direction. However, in transverse waves, the vibrations are at a right angle to the direction of wave travel. So in longitudinal waves, the vibrations are parallel to the direction of wave travel. However, in transverse waves, the vibrations are at right angles to the direction of wave travel. And moving on to another distinction between different types of waves, we have mechanical waves and we also have electromagnetic waves. So magnetic waves cause oscillations of particles in a solid, a liquid, or a gas, and they must have a medium to travel through. So going back to our examples before, the water ripples is an example of a mechanical wave because they're causing that oscillation within a liquid in that example. In contrast to this, we also have electromagnetic waves, and these cause oscillations in electrical and magnetic fields. So they don't necessarily need a medium, so a solid, liquid, or gas, to travel through, unlike the mechanical waves. So mechanical waves, they need the medium to travel through, whereas electromagnetic waves, they cause oscillations in electrical or magnetic fields. We're now going to look at different parts of a wave. We're going to discuss all of these terms and what they mean, because they're used to describe different parts of a wave. So the rest position, which is the first definition we have on this list. A rest position is the undisturbed position of particles or fields when they are not vibrating. So it's where they are when they are not vibrating. So it's the undisturbed position of particles or fields when they are not vibrating. So it sounds like what it means really. It's just a rest position when those particles or fields are not vibrating. Now, moving on to the second definition we have here, we have displacement. And displacement is the distance that a certain point in the medium has moved from its rest position. So if it starts here in the middle, if it moved to here, the distance between these 2 points is the displacement. It's the distance that a certain point in the medium has moved from its rest position. So it's just that distance of movement within that medium. We then have peak, which is the highest point above the rest position. So it's the highest point above that rest position. And then we also have trough, and the trough is the lowest point between the rest position. So we have the peak, which is the highest point above the rest position, and we also have the trough, which is the lowest point below the rest position. Now, the next point we have here is the amplitude. So this is the next word on this list here. You can see that one there. And that is the maximum displacement of a point of a wave from its rest position. So it's the maximum displacement. And you'll remember that displacement was the distance that a certain point has moved from its rest position. Now, amplitude is the maximum displacement of a point of a wave from its rest position. So it's the maximum displacement of a point of a wave from its rest position. The next word we have is wavelength, and that is the distance covered by a full cycle of the wave. And it's usually measured from peak to peak or trough to trough. Now, don't worry, we'll be looking at a wave diagram in the next slide. So we're going to look at these in practice. So don't worry if you're a bit confused by what I mean there. But the wavelength is the distance covered by a full cycle of a wave. We also have time period, which is the time taken for a full cycle of a wave, which is usually measured from peak to peak or trough to trough. So that one is the time taken, whereas wavelength is the distance covered by the full cycle. Time period is the time taken for a full cycle of the wave. And the last one we have on this list here is frequency, which is the number of waves passing a point each second. So it's the number of waves coming through a particular point per second. Now we're now going to look at all of these in practice. So you can see here we have a diagram, and this red line here is the wave. So this red line is the wave here. And to begin with, we're going to start with rest position, which we began with before. You remember that the rest position was the undisturbed position of particles or fields when they're not vibrating. And you can see that here. So this here on the left is the rest position. And that is the sort of ground level. And this is what this line represents. And this is where there is no vibrations occurring. The next thing on this diagram you can see is the peak and the trough. So you remember before we spoke about peak and trough being the highest and lowest points above and below the rest position. And you can see that here. So the peak here, this is the highest point above the rest position. And then the trough is the lowest point below the rest position. The next thing on this diagram is the amplitude. And you'll remember that the amplitude is the maximum displacement of a point of a wave from its rest position. So here is the displacement, and this point here is the maximum displacement of a wave, a point of a wave, sorry, from its rest position. So this, the height of this, the height of this movement above the line is the amplitude. So this distance here represents the amplitude, and it's the maximum distance, so it's up to that peak point. It's the maximum movement from the rest position. Now, the next thing on this diagram is a wavelength, and as we said before, a wavelength is the distance covered by a full cycle of the wave, and it's usually measured from, as we said before, peak to peak or trough to trough. And you can see that here. So this, we have two peaks here, and the distance between that is the wavelength. So this shows the wavelength. You can also do it from trough to trough, as we mentioned before. So again, this is also showing a wavelength. So it's showing a whole wave. And you can also, it doesn't have to be the peak or trough. As you can see here, you can also measure it from two equivalent points on the wave. So all of these show the wavelength, which is a full cycle of the wave. Now, moving on, we're going to talk about time periods, which you mentioned before. And we said before that this is the time taken for a full cycle of a wave. And again, it's usually measured from peak to peak or trough to trough. Now, yeah, the time taken of a wave can be calculated, as we can see here, from this equation. So the time period of a wave can be calculated using this equation. And the equation is, as you can see here, is time period equals 1 divided by the frequency. So time period is equals 1 over the frequency. And that is how you calculate the time period. And this is where the time period is measured in seconds and the frequency is measured in hertz. So this top equation here is just the simplified shorthand version of this full equation. We have a capital T signifying the time period, and we have the F representing the frequency. And the units, as I just said, are seconds for time period and frequency for hertz. Now we're now going to look at an example of this. So you could get a question like this, saying calculate the time period of a wave with a frequency of 400 hertz. Now you remember the equation is time period equals 1 over frequency. So we're looking at the time period, so we need to do 1 divided by the frequency. And we're told here that the frequency is 400 hertz. So we do 1 divided by 400. And the answer to that is 0.0025. And that we measure that in seconds. So don't forget your units. So it's measured in seconds, which we've got here. So the time period of this wave in this example is 0.0025 seconds. And that is your answer. Now, we're now going to move on to looking at wave speed. So you can see here again, we have another equation for this. And you can work out you can use this formula, to work out the frequency and wavelength if you're given the other two values as well. So it's a really useful formula. And you can work out the formula by covering up the value you need. So if you wanted to work out the wave speed, you would cover this symbol here, which represents wave speed, and you would see that the equation is the frequency times the wavelength. And similarly, if you wanted to work out the frequency, you would cover up the frequency, this F here, and you would get the wave speed divided by the wavelength. This line here represents division. So it can be really used, this triangle is very useful for working out all of the components we can see on our screen, so the wave speed, the wavelength, and the frequency. So we've got another example here on the left-hand side, and you can see it says calculate the speed of a wave where the frequency is 50 hertz and the wave speed is 6 meters. Now, the first thing you should always check is that things are in the correct units. And you can see here that hertz is the measurement for frequency, and we also have hertz here, so that's fine. And we also have meters, which is the measurement of wavelength. If, for example, they gave you the wavelength in centimeters or even millimeters, you would have to convert that into the correct unit before you did the calculation. Otherwise, you're going to get the wrong answer. So going back to the example, we're working out wave speed. So we need to do frequency times wavelength. So we cover the V for wave speed, and we know that the equation is frequency times wavelength. And we're given those values here, they are 50 and 6 respectively. So we do 50 times 6, which gives us 300 meters per second. So wave speed of this particular wave is 300 meters per second. And again, just remember to include your units whenever you are doing calculations. We're going to look at one final calculation, and that is measuring the speed of sound in air and water. And again, we have one of these triangles, which you can use to work out any of these components. So we have S, which represents the speed measured in meters per second. We have the distance, which is measured in meters, and we have the time, which is measured in seconds. And again, just as before, we cover up the letter which we want to find out, and then it shows us the formula. So say if we wanted to work out the speed of the sound in air or water, we would cover that S, and we would see that the equation is then the distance divided by the time. And similarly, you can cover up the other aspects to ensure that you can work out the correct equation. And just a bit of context for this slide, the air is in fact made up of tiny particles. The air around you is made up of tiny particles. And when sound is created, the air particles vibrate and they collide with each other. And this causes the vibrations to pass between the air particles. And these vibrating particles pass a sound through a person's ear and vibrate their eardrum. And that is how sound is carried in air and in fact in water as well. And you can work out, as I said, the speed of sound using this formula. And you can also, again, work out the distance and the time in a similar way by covering up that letter you want to work out, and it gives you the formula. Now, this is just a quick example of measuring the speed of sound in air and water. This one is in fact in air. So we have Kat, who is 400 meters away, records a 1.2 second time difference between seeing my hand signal, and hearing the bang of my starting pistol for the race. Now, we're working out the speed here. We want to know what the speed is of that sound traveling, and we are given the components needed here. So we know that speed is distance over time by looking at the triangle. We cover up the S and we see it's distance over time. And we are given the distance here. She's 400 meters away, And we also have the time difference here, which is 1.2 seconds. So you know that then it is 400 divided by 1.2, which gives us 333 meters per second. And I've rounded that answer here to 3 significant figures. So the answer to this question is 333 meters per second. Now that is the last calculation we'll be looking at, and this brings us to the end of this lesson. I hope that it's been informative. We've looked at different types of wave, we've looked at the different labels to put on a wave diagram, and we finally did some calculations regarding waves. I hope this has been useful and that you have enjoyed this lesson. Thank you for watching. Goodbye.